Look, I need to tell you something, and I need you to really hear it right now, right this second. You are sitting on a chair, or maybe a couch, and the chair is not falling through the floor. Good, that is normal. The floor is solid, the earth is solid beneath it. And all of that solidity, all of that nice comfortable structure depends on the laws of physics behaving themselves. Space goes in three directions. Time moves forward. Gravity pulls things together in a sensible, predictable way. That is the deal. That is the arrangement. And it works. It works beautifully almost everywhere in the universe, except in one place. There is a place where space stops being space, where time stops going forward and starts going. Well, I'll get to that. Where the laws of physics, the very equations I spent my life working with, scribble out a number, and that number is infinity. And infinity is not an answer. Infinity is the equation throwing up its hands and saying, I give up. I don't know. That place is the inside of a black hole. And what happens in there is not just strange. It is, I think, the most important unsolved problem we've got. But before I can explain what goes wrong in there, I need you to understand what you think space and time are, because you've got a picture in your head. And the picture is wrong. Not a little wrong, really, deeply, fundamentally wrong. And that is okay. I had the same wrong picture for a while. Everyone does. So here is what you probably think. You think space is like a room, a big empty room. Things exist inside the room. Planets, stars, you, me, but the room itself just sits there. It is the container. It doesn't do anything. It is just there. And time, you think of time as a clock ticking in the background, tick, 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 same rate for everybody. Newton thought this way. And listen, Newton was no dummy. This picture works fantastically well. It got us to the moon. You can build bridges with it. You can predict eclipses for 300 years. This was the picture, and nobody had any reason to question it. Then Einstein comes along. Now, I want to be careful here because people throw Einstein's name around and they say he proved everything is relative. And that is, no, that is not what he did. What Einstein did in 1915 was much more specific and much more disturbing. He said, that room you think you are living in, that fixed, rigid, empty room of space, it is not fixed. It bends, it stretches, it warps, and it does this in response to mass, in response to stuff being in it. The container is being pushed around by the contents, which is, think about that for a second. Imagine you put a bowling ball on a table, and the table itself changed shape, not the tablecloth. The table, the actual hard surface, rearranged itself because of the ball. That is what mass does to space. And here is the part that really gets people: gravity. The thing that holds you in your chair right now is not a force. I know your teacher told you it is a force. I probably told some students it is a force, at least on the first day before I corrected myself. But in Einstein's picture, gravity is geometry. The earth doesn't reach out and pull you down. The earth bends the space around it, and you are just following the bend. You are walking in a straight line through curved space. You feel like you are being pulled, but you are not. You are sliding along a curve in space-time that the earth created just by being massive. Now, this isn't speculative. I want to be clear about that. General relativity has been tested over and over and over. GPS satellites have to correct for it. If they didn't account for the curvature of space-time around the earth, your phone's map would drift by about 10 kilometers a day. This is real. This is tested. This works. And it raises a very uncomfortable question. If space-time can bend, if it can warp and curve and respond to mass, what happens when it bends too much? What happens when you put so much mass in such a small space that the bending becomes? Well, let me tell you what happens. But first, I've got to tell you about stars, because that is where this whole mess starts. A star. See, a star is really just a balancing act, and it is a violent one. You've got gravity pulling everything inward. Every atom in the star wants to fall toward the center. If gravity had its way, the whole thing would collapse into a tiny point. But it doesn't, because the star is also a nuclear furnace. Down in the core, hydrogen atoms are smashing together, fusing into helium, releasing enormous amounts of energy. That energy creates pressure, outward pressure, that pushes back against gravity. And for millions, Sometimes billions of years, these two forces they balance. The star sits there, perfectly stable, not because it is calm. It is a thermonuclear explosion the size of, well, our sun is 1,000,000 times the volume of the Earth. So it is a really big explosion, but it is an explosion that is trapped by its own gravity. A bomb in a cage where the bomb is also the cage. But here is the thing. Fuel runs out. It always runs out. The star burns through its hydrogen, starts fusing helium, burns through that, fuses carbon, and so on up the periodic table until it hits iron. And iron is the end of the line. You can't get energy out of fusing iron. So the furnace goes out. The outward pressure drops. And gravity, which has been waiting very patiently this whole time, wins. Now what happens next depends on how big the star is. And there is a wonderful story here. In 1930, a kid, he was literally 19 years old, named Subramanian Chandrasekhar, was on a ship from India to England. He was going to Cambridge to start his graduate work. And on the boat, he did a calculation. He worked out that if a dead star, a white dwarf, has more than about 1.4 times the mass of our sun, the quantum mechanical pressure of its electrons can't hold it up. Nothing can hold it up. It will collapse. He gets to England. He presents this to the scientific community, and Arthur Eddington, who was a very famous, very respected astrophysicist, stands up and essentially laughs at him. In public, says nature surely wouldn't allow such an absurd thing. And look, I have a lot of opinions about how science sometimes treats young people with good ideas, but I'll save that for another day. The point is, Eddington was wrong. Chandrasekhar was right. Nature does not care whether Arthur Eddington is comfortable. Nature does what the math says. And the math says if the star is massive enough, the collapse doesn't stop. So the star falls inward, and as it does, the space-time around it curves more and more and more. And at a certain point, at a certain radius, which we call the Schwarzschild radius, something happens to the geometry that is. Okay? Let me try to say this clearly. You know how normally in space you can move in any direction. Left, right, up, down, forward, back. You have choices. At the Schwarzschild radius, the curvature of space-time becomes so extreme that all the available paths, every single possible trajectory, including the path that light would take, bend inward. There is no outward direction anymore. It is not that something is blocking you. It is not a wall. It is that the geometry itself has rearranged so that outward doesn't exist as a concept. It is like, let me think of a good way to say this. Imagine you are on a treadmill, running as fast as you possibly can, and the treadmill is moving backward faster than you can run. You are not slow. You are running at full speed. But you are not making progress because the ground itself is working against you. That is what happens to light at the event horizon. Light is moving at the speed of light. It is going as fast as anything can go. But the space-time it is moving through is curved so severely that full speed isn't enough. The event horizon is not. I want to be really clear about this. It is not a wall. It is not a surface. It is not a physical thing. If you were falling into a sufficiently large black hole, you would cross the event horizon and you would feel nothing. Nothing. No bump, no flash. No sign that says, welcome to the point of no return. Locally, meaning in your immediate neighborhood, everything would look completely normal. You could check your watch. You could scratch your nose. Physics would seem fine. The event horizon is not a local phenomenon. It is a global one. It is defined by the fact that once you are inside, no signal you ever send will reach the outside universe again. You don't know you've crossed it until it is too late. Actually, that is not right either. You never know you've crossed it. There is no way to detect it from the inside. It is a boundary in your future, not in your space. And what happens inside, okay? This is the part where I need you to really concentrate, because this is where things get, honestly, kind of insane. Inside the event horizon, space and time trade jobs. Now wait, let me say that more carefully, because that sounds like I am being dramatic, and I am not outside a black hole. You have freedom to move in space, left, right, Up, down, your choice. But you have no freedom in time. Time goes forward. Period. You don't get to choose. You can't stop it. You can't reverse it. You can't even slow it down from your own point of view. You go forward in time whether you like it or not. That is how time works. Inside the event horizon, the radial direction, the direction toward the center of the black hole, mathematically takes on the properties that time had, and time takes on properties that space had. So moving toward the center is no longer a choice you are making in space. It is the passage of time. You fall toward the singularity the same way you fall toward next Tuesday. You can't avoid it. Not because something is pushing you, because it is the future. Every possible path through time leads there. Turning around makes as much sense as turning around in time, which is to say, no sense at all. And at the end, at the center, general relativity predicts a singularity, infinite density, infinite curvature. The equation spits out infinity, and look, when an equation gives you infinity, that is not an answer. That is the equation telling you it is broken. It is like asking someone a question, and they just start screaming. That is not a response. That is a breakdown, and that is exactly what the singularity is. It is general relativity breaking down, confessing that it doesn't know what happens at the center of a black hole. The theory that predicted the black hole's existence cannot predict what happens at its core. The theory that works everywhere else in the universe, from GPS satellites to the expansion of the cosmos, writes a suicide note at the center of its own creation. Now, most physicists, and I'd count myself here, don't think the singularity is a real physical thing. Infinite density probably doesn't actually occur. What the singularity is telling us is that we need a better theory, a theory that combines general relativity with quantum mechanics, a theory of quantum gravity. We don't have it yet. The singularity is not a place, it is a question mark. But let me make this more concrete. Let me put you there. Imagine two people, you and your friend. Your friend is going to stay far away from the black hole, safe on a space station. You are going to fall in free fall. No rockets, just you and gravity. From your perspective, the fall feels normal. You are floating, weightless. You cross the event horizon and notice nothing. Time passes normally for you. Depending on how big the black hole is, you might have minutes or hours before you reach whatever's at the center. That is your experience. Your friend's experience is completely different. Your friend watches you fall toward the horizon, and you start to slow down. Your image stretches. The light coming from you shifts to redder and redder wavelengths. You get dimmer. You get redder. You appear to freeze right at the edge of the event horizon, getting fainter and fainter, but never quite crossing. Your friend could wait 1 billion years and still see your ghostly fading image hovering at the boundary. Now here is what gets me. Both of these stories are true. Not one is real and the other is an illusion. Both are physically valid descriptions of the same event from different frames of reference. You crossed, your friend never saw you cross. Both are correct. Reality apparently does not have a single story to tell about this. It has got two, and they contradict each other, and they're both right. If that doesn't make you uncomfortable, you are not paying attention. And let me give you something to feel in your body, because physics should never be just abstract. Imagine you are falling in feet first. Your feet are closer to the center than your head. Gravity is stronger at your feet, so your feet get pulled harder than your head. This difference, this tidal force stretches you lengthwise. You are being pulled apart like taffy. Sideways, you are being squeezed together because all the gravitational lines converge toward the center, stretched long and squeezed thin, physicists. And we have a real gift for naming things called the spaghettification. I am not joking. That is the actual technical term. Now here is a fun detail. If the black hole is small, say a few times the mass of the sun, the tidal forces are so extreme that you'd be torn to atoms long before you reach the event horizon. You'd be spaghetti before you even got to the interesting part. But if the black hole is supermassive, billions of solar masses, like the ones at the centers of galaxies, the tidal forces at the horizon are actually gentle. you'd cross comfortably. You'd be fine, intact, conscious, and completely doomed. Everything about you, every atom, every photon, every bit of information that describes who you are would be inside. Which brings us to the really hard problem, the one that has been keeping physicists up at night for 50 years. In 1974, Stephen Hawking figured out something that made everything worse. He was working with quantum field theory near the event horizon. Now, I should say, this is a semi-classical calculation, meaning he used quantum mechanics in a curved space-time background, but didn't quantize gravity itself. So there are caveats. But what he found was that black holes aren't perfectly black. They glow. Faintly, they emit a very weak thermal radiation, random, featureless heat that slowly carries energy away from the black hole over a fantastically long time. We're talking numbers with more zeros than you'd want to write. The black hole would radiate all its energy and evaporate, poof, gone, nothing left. But, and this is a really big but, the radiation is thermal. Random, it carries no specific information about what fell into the black hole. It is like heat coming off a stove. The heat tells you the temperature, but it doesn't tell you whether you are cooking chicken or pasta. So if the black hole evaporates completely and the radiation is featureless, where did the information go? Everything that fell in stars, planets, books, people, had a precise quantum description. That information has to be somewhere. Quantum mechanics has a rule, a very deep rule. Information is never destroyed. You can scramble it, you can hide it, you can make it practically impossible to retrieve, but you cannot erase it from the universe. So general relativity says the information is gone. It fell behind the event horizon and the black hole evaporated. Quantum mechanics says information can never be gone. Both of these are foundational theories. Both work spectacularly well everywhere else. And here, at the black hole, they flatly contradict each other. This is the information paradox. And I want to be honest with you, after 50 years, nobody has solved it. There are proposals, some very clever proposals, but no solution that everyone agrees on. Hawking himself went back and forth on this in 2004, and this was a big deal at the time. He publicly conceded that information is probably preserved somehow, that it gets out. He didn't have a complete mechanism, but he pointed toward an idea that had been developing for about a decade called the Holographic Principle. Now this idea, and I want to flag this as speculative because it is this idea, originally from Gerard T. Hooft and developed by Lenny Susskind, says something really wild. It says that all the information about a three-dimensional volume of space can be completely described by data on its two-dimensional boundary surface, like a hologram. You've seen holograms, flat piece of film, but it encodes a three-dimensional image. The holographic principle says maybe reality works like that. Maybe everything happening inside a black hole is fully encoded on the event horizon's surface. Maybe three-dimensional space is. Let me be careful. Maybe our experience of three dimensions is in some deep sense a projection of a lower dimensional reality. Now, is this true? I don't know. Nobody knows for certain. It is mathematically very compelling in certain special cases, but it hasn't been proven in general. And even if it is right, it opens up problems of its own. In 2012, 4 physicists, Almheri, Maroff, Polchinski, and Sully, people call them AMPS, they published a paper that basically set fire to the whole fragile compromise. They showed that you can't have all 3 of the following things at once. 1, information is preserved in the Hawking radiation. 2, the event horizon is smooth and harmless for someone falling through. 3, quantum field theory works normally outside the black hole. Pick any 2. The third one breaks. And if you pick options 1 and 3, if you insist that information is preserved and quantum field theory works, then the event horizon is not smooth. It is a wall of high-energy radiation, a firewall. You'd hit it and burn up the instant you tried to cross, which directly contradicts general relativity, which says crossing the horizon should feel like nothing at all, so you are stuck. You've got 3 principles that all seem right, and they can't all be right. Something has to give, and nobody, I mean nobody, agrees on what. This has been going on for over a decade now, and there is no consensus. Every proposed solution kills something that physicists thought was sacred. That is where we are. That is the honest state of the field. Now, I know some of you are sitting there thinking, okay, but are black holes even real? Maybe this is all just math, equations on a chalkboard. And 10, 20 years ago, that would have been a reasonable thing to say. It is not reasonable anymore. We have seen them. In the center of our galaxy, there is a star called S2. We've watched it orbit an invisible object for over 20 years. It moves at more than 10 million kilometers per h-hour. The orbit traces out a path that matches precisely what general relativity predicts for a black hole of about 4 million solar masses. That object is called Sagittarius A star. In 2015, the LIGO detector picked up gravitational waves, actual ripples in space-time, from two black holes smashing together over 1 billion light years away. The signal matched the predictions perfectly. In 2019, the Event Horizon Telescope, which is basically a telescope the size of the Earth, stitched together from radio observatories on different continents, produced a direct image of the shadow of a supermassive black hole in the galaxy M87. Not an illustration, not an artist's impression, a photograph. Black holes are real. They're as real as the chair you are sitting on. We've measured them, heard them, and photographed them. But, and here is where I'll give some ground to the skeptics, the singularity is almost certainly not real. When the equation gives you infinity, that doesn't mean infinity actually happens. It means your theory has been pushed past its limits. This has happened before in physics. Classical electromagnetism says the energy of a point charge is infinite. That is obviously nonsense, and quantum mechanics resolved it. The singularity is the same kind of red flag. It is general relativity saying, I can't handle this situation. Something else takes over here, something I can't describe. The singularity is not a physical infinity at the center of a black hole. It is a confession of ignorance, a question mark. And it has been sitting there for 100 years, waiting for someone to develop the mathematics to see past it. So what does all of this actually mean? What are black holes telling us? Here is what I think, and look, this is partly my opinion, so take it for what it is worth. General relativity and quantum mechanics are the two best theories we have ever built. Full stop. General relativity handles gravity, space-time, the large-scale structure of the universe. Quantum mechanics handles atoms, particles, forces, the small-scale stuff. Both are tested to ridiculous precision. Both work beautifully in their own domains. And for most of the universe, they never need to fight each other. Gravity matters at big scales. Quantum mechanics matters at small scales. They stay out of each other's way. A black hole is the one place where they can't avoid each other. At the singularity, gravity is extreme and the scale is quantum. At the event horizon, the information paradox forces both theories to make claims about the same process. And the claims contradict. The firewall argument makes it even worse. This isn't a small technical issue. This is two pillars of physics walking into the same room and throwing punches, and one of them, maybe both, is going to have to change. The resolution, whatever it turns out to be, will not be minor. It will not be a small adjustment. It is going to be a revolution on the scale of relativity itself, maybe bigger. And here is the part that really keeps me up at night, in the best possible way. What black holes might be telling us. And again, I am speculating here, this is not established, is that space and time are not fundamental, that they're not the deepest layer of reality. Einstein showed us that space and time are dynamic, they bend and curve. Black holes show us that they can swap roles, that time can end, that the fabric of space-time can curve so hard that our best theory shatters. The information paradox suggests that maybe the resolution involves space and time being emergent. Not the real ingredients of the universe, but approximate descriptions that arise from something deeper, something like quantum information, something like entanglement, some underlying structure that produces what we call space and time, the way temperature arises from molecules bouncing around. Temperature is real. You can feel it, but it is not fundamental. It emerges from something beneath it. Space and time might be the same kind of thing, real, useful, measurable, but not the bottom layer. We don't have this theory. I want to be completely clear about that. We're guessing, educated guessing, informed by a lot of mathematics. But guessing, the black hole is sitting there, patient and silent, holding the answer inside a region that our current theories cannot describe. And I don't find that frustrating. I find that wonderful, because that is what physics is. It is not a collection of answers. It is a way of finding the next question. And the black hole, this thing that bends space, stops time, swallows light, evaporates into featureless heat, and forces our two best theories into open war. The black hole is the best question we've got. It is not a monster. It is not a cosmic villain. It is a mirror. It shows us, with perfect precision, exactly where our understanding ends. And the day someone sees past that boundary, the day someone writes the equation that makes sense where Einstein's equation breaks, that will be the day we understand what space and time actually are, not what they look like, not how they behave, what they are. We're not there yet. But the fact that we know exactly where to look, that we can point to the precise spot where the known laws fail, that is not a defeat. That is the most exciting thing in physics.